Hello, I welcome you all in the course Refrigeration and Air Conditioning, and today we will continue our discussions on cooling load. There are several load calculation methods. We will discuss them one by one. We will not go into the details because it will take a lot of time. Sol air temperature I would like to mention, fans, sensible heat gate coefficient and residential air conditioning. Load calculation methods, there are several load calculation methods. A number of softwares are available in market. You simply give the input data and you will get the load in the building. And most of the professionals, they are using these softwares which are available in market. But there are some fundamental methods like heat balance method. Now heat balance method, also known as HB method, it is exact solution of the method. I mean conduction, convection, radiations, heat transfer from each wall, outside wall and each wall of the room, from one room to another, from roof, from floor, from everything. I mean it is a complete heat transfer exercise and it is an iterative method. I mean it is iterative method but it gives us this exact solution. Similarly transfer method also, transfer function method also, this involves mathematical equations and iterations and we get heat load in the building. Total equivalent temperature difference method and cooling load temperature difference, cooling load factor, these two methods are used by the professionals to find the load in the building. Now in these methods there is one term which is known as Sol air temperature. Outside temperature is something that is TO and inside temperature is TI. But what happens when solar radiations fall on the building? Part of these radiations is reflected and part of these radiations is absorbed by the building and they are these radiations are subsequently transmitted through the buildings. Now if you look at the architecture of the old buildings in India, we have heavy type of construction. If you go to the Europe or US, you will find light type of construction. They have light construction because in their building most of the times they do heating. Most of the time they do heating and in order to save energy, they prefer to have lower thermal capacity of the building so that when heating the building, minimum heat is absorbed by the building. At the same time, the entire building is insulated. Wall insulation, roof insulation, everything they do so that heat loss from the building is minimum. Heat loss means there is a loss of energy. So a lot of insulation work is done by them, but here in India, our construction is heavy type of construction and the walls have high thermal capacity. Normally there is a 9-inch wall and plus half-inch plaster on the both side. So it becomes a 10-inch wall. This is a typical size of the wall and overall heat transfer coefficient U for the wall is approximately 2.2 or 2.3 kilowatt per meter square Kelvin depending upon the material used, and overall heat transfer coefficient. Yes, in heating, in cooling load calculations, the U factor, it is known as U factor. U factor is very important. Now U factor, if you know the U factor, immediately you can find the value of Q is equal to UA delta T. You know the outside temperature TO, inside temperature, area of the wall and U factor. So table of U factors are available in air conditioning because everything you are not expected to calculate. So if you refer the data book, right, if you refer the data book or if you issue a handbook of fundamentals, you will find that for everything tables are given. So if you want to have U values, you will get from those tables area of the building, area of the wall of the building and temperature difference. This will give the heat transfer. So this U factor is giving for everything, right? Anything through which the heat transfer is taking place, the U factor is given, and the moment you have the value of U factor, you can immediately find the value of Q by just simply having the information about 2O and TI and area of that part. Now we were talking about Sol air temperature. So Sol air temperature comes into the picture when radiations are falling on the wall of the of a building. Part of the radiations are reflected and part of the radiations are absorbed by the building. Suppose radiation I is falling on the building and absorptivity of the building is alpha, absorption coefficient is alpha, right? Outside film coefficient. Now, when we calculate overall U factor or overall heat transfer coefficient, so U is equal to 1 by FO plus 1 by Fi plus x1 by k1 plus x2 by k2, you say x3 by k3 and so on. Now, FO is film coefficient. It is the ratio of, film coefficient is the ratio of heat transfer divided by outside air temperature minus temperature of the wall divided by area of the wall. This is film coefficient. It is same as heat transfer coefficient. So, this film coefficient of outside, say outside wall, if there is a calm air, suppose in this room there is no fan, there is no air movement, it is approximately, we assume 5 to 7 watts per meter square Kelvin. If air is blown with with not very high speed, then we can go up to 15 watts per meter square. For this also tables are available. If the air is blowing over a surface with this velocity, this is going to be the value of FO or film coefficient. Similarly, we can find the value of Fi. Now, Xi is the thickness of, suppose there is a brick. So, thickness of the brick, thermal conductivity of the brick, thickness of outer plaster, thermal conductivity of outer plaster, thickness of inner plaster, thermal conductivity of inner plaster, and all this give the value of U factor. But when we start designing the system in the data book, if we give the specification of the building, immediately we can read U factor from the data book. So, we do not have to do these calculations. Now, regarding soil air temperature, we will take FO, outside film coefficient, TO minus TWO, outside wall temperature. Now, this is going to be equal to QO per unit area. This is heat flux or QO per unit area. Now, QO can also be assumed as some fixture temperature. This is known as soil air temperature. Or TO. This is some fixture temperature, soil air temperature, and this is also QO. Now, if you compare these two equations, so you will be getting soil air temperature is equal to TO plus alpha I by FO, right? Now, this temperature will be used, now this soil air temperature will be used for heat transfer related calculations, because outside temperature may be 43 degrees centigrade, but the radiations falling on the wall, will increase the temperature of the wall much more than 43 degrees centigrade. We can take some fictitious values here and then we can find how much temperature increase will be there. Suppose outside temperature is 35 degrees centigrade, radiations falling, say let us say 300 watts per meter square multiplied by 0.9, this is absorption, 90% of the radiations are absorbed. Film coefficient, suppose air is flowing over the external wall, then the value of F is 20. Now, in this case, if we solve this equation, we are going to get 48.5 degrees centigrade. Now, for the heat transfer purpose, for heat transfer calculations, instead of using 35 degree centigrade temperature, we are going to use 48.5 degree centigrade temperature. So, we can find soil air temperature as 48.5, however, the outside temperature is only 35 degree centigrade. Now, another method is radiant time series method, RTS method. Now RTS method is the latest one, and you will be wonder to know why we are already having so many methods, so why there is another method. This method is latest method because nowadays architecture of the buildings have changed. Earlier fenestration area was not much, it was around 50%, 15%. Fenestration. This is a term which is frequently used while designing a system. Fenestration. Fenestration is the area like windows, okay, through which the light can come, and if you open the windows, the air can also come in. So, air panels, windows, sorry, the window panels, they are known as fenestration in the building. Normally, this glass work was approximately 15%, but now it has increased. It has gone up to 50%. Now, in modern buildings, you must have seen there is a frame, and they use a lot of glass. The use of high percentage of glasses in the building brings in the heat transfer through transmission of solar radiations into the building. When these solar radiations are transmitted into the building, they heat up the articles occupying the building, and then from these heated articles the radiation takes place, and there is a time lag between these two. That is why a new method has been adopted, and this is also a very accurate method, radian time series method. This method can also be seen in details in ASHRAE 2005 handbook. Residential load factor method, because many of the cases we have to design an AC system for residences only, right. So, there is a residential load factor method where we simply calculate the area and cooling factor. Cooling factor, there are number of tables in this method. This method actually has limited application. It is mainly it is applicable, or mainly it is used for the buildings in a western type of architecture. But if we use for our architecture, our heavy construction type of buildings, we will get some conservative estimate of the cooling load. Conservative estimate means the actual cooling load is 10 ton. Through this method, we may be getting 10.5, 11 or 12 tons. So, that is a conservative estimate of cooling load. So, but this method can also be applied. I mean, and this is very easy to use. You just have to take simple area of the building, and cooling factor you have to take from the tables. There are different tables, there are n number of tables, and from these different tables you just keep on putting the features of the building, and you will get a cumulative cooling factor. Just cumulative factor multiplied by the area, and you will get the cooling load in the building. And this CF is, we can say this CF is nothing but a product of U factor and delta T. This CF is the product of U factor and delta T. In fact, just we have to give outside condition and inside condition. Inside conditions are also, I mean, they are standard in a building. So, we get cooling factor, and this method is easier to use. But it is applicable only for residences, residential buildings. For multi-story building and commercial buildings, we will have to go for some other methods stated above. Now, solar heat gain coefficient, yes, solar heat gain coefficient is rated with the glass. It tells us the value of solar heat coefficient is like other coefficient, it is varies between 0 to 1. And this coefficient tells us that how much solar heat is transmitted to the glass, through the glass. If it is a haze glass, this coefficient may be of the order of 0.2. If it is a clean glass, we want heating of the building, this coefficient may be 0.9. But it varies between 0 to 1. 0 means opaque, there is no transmission. So, for every glass, there is a solar heat gain coefficient, and there are a variety of glasses in the market. So, for each glass, you can find in that table is also available in data books. You purchase any air conditioning data book, you will find solar heat gain coefficient tables. U factor, I have already explained you. Now, visibility transmittance, this is also related with the quality of the glass. So, visibility transmittance means how much visibility or how much light has been transmitted to the glass for for the purpose of visibility in the room. Now, unique features distinguish residence from other type of building are as follows. Yes, because I told you earlier also that the residential air conditioning is different. In residences, the addition of latent heat load is very less. I mean, you will find, or if we talk in terms of sensible heat factor line is almost horizontal, almost, it is 0.95 or 0.96, it is almost horizontal. In residences, latent heat addition takes place only in the kitchens or through occupants to certain extent, and rest of the features like small, I have already explained you, small internal heat gains, various uses of a space, varied uses of a space. So, I mean, a space can be used for variety of purposes, fewer zones. We like to have a building, I mean, the entire house almost at the same temperature. There is less number of zone, or there are no zone in the houses. Great distribution losses are more in residential buildings. Okay, partial loads are there, sometimes occupancy is there, sometimes occupancy is not there. Some issues are related with the dehumidification in the buildings. Now, while designing a building, we need certain data, certain information about the building. Now, information in the form of gross area. Gross area means outside area of the building, length into width or length height. Fenestration area, part of the building which is occupied by the fenestration, net area, the difference of gross area and fenestration area, volume of the building, construction characteristics of the building, U factor of the building, again fenestration of the building, how much infiltration is taking place, the order of air tightness of the building. Air tightness I have already discussed in my previous lecture. Load from opaque surface has to be calculated, load from fenestration has to be calculated, and interior shading, outer and interior shading. Suppose there are trees or there is another tall building in the vicinity of the building. So, there is one building, there is another tall building in the vicinity of the building. So, shadow of this building will also come on this building. This has to be considered. Further, we should remember if north, south, east, west, the maximum load on the building comes on southwest side, because if you look at the location of India on a globe, it is in the northern hemisphere spreading from 7 north to 37 north, and Tropic of Cancer passes through India. Now, Tropic of Cancer is 23.5 north, right. So, it passes through India, it passes near, I mean, city Allahabad and Jabalpur. So, if you, for example, Roorkee is north of the Tropic of Cancer. So, sun will never be overhead at Roorkee, because the sun at the summer solstice, after 21st of June, sun will retreat from this Tropic of Cancer. Sun will retreat from Tropic of Cancer. So, sun will never be overhead of Roorkee. But if you look at the sun is rising from here, setting here in equinox like 22nd March and 23rd September, or 22nd or 23rd September. So, we will find that sun is rising in the east. From here, it is going to the south and then is coming to the west. So, sun, suppose I am located Roorkee here. So, sun is in Roorkee, sun is rising in the east, going to the south. It appears so, it does not happen, but it appears so that it is going to the south and it is coming to the west, and most of the heating comes on southwest wall. If your location in the southern hemisphere, the situation will be different. The most load will come on which wall? This is east west, this wall. Most of the load will come on this wall. So, this has to be taken into account while designing a system, that what order of shading or is getting, and for interior shading also. Suppose we want to reduce load, solar load in a house, proper curtaining, thick curtains can also reduce solar radiations coming to the house. So, there are many ways of passive techniques, they are known as passive techniques. There are many passive techniques which can help us in reducing loads in the building. Suppose you have a rooftop garden will also, because most of the heat comes from the roof. So, if you are having a rooftop garden, the rooftop garden will also reduce the heat transmission to the room from the outside. Now, after this I will take one example of, suppose this is a classroom, I will not solve this entirely, I will partially solve it and later on you can do it by yourself. Suppose in a classroom there are 100 students, right? There are 100 students, I have to find a load, there are 100 students. First of all I will put the psychometric chart. So, very popular outside condition is 34-28. So, 34 dry bulb, it means 34 dry bulb temperature and 28 wet bulb temperature, 26, 27, 28 and 34. Yes, relative humidity is approximately 65% and 34 degrees centigrade outside temperature. Now, this I'll draw here also. Right, 30, I will write here dBT 34 degrees centigrade and wet bulb temperature is 28 degrees centigrade. So, we have taken 28 degrees centigrade wet bulb temperature line and 34 degrees centigrade dry bulb temperature line, and the inside is 24 50% relative humidity. I want to maintain in this classroom 24 degrees centigrade temperature and 50% relative humidity. Now, either through software or through manual calculation, I calculate the value of solar gain. Let us take solar gain. Some solar gain is 5 kilowatt, suppose it is 5 kilowatt. Solar heat coming from the glass, is, let us say, 4 kilowatt. Occupants 100, okay, let us take 60 is a standard classroom, 60 students. Now, tube lights, let us say there are 10 tube lights. Fans, there are 8 fans, and some load also, sensible load from, say, let us say LCD project or some computer, maybe let us say 0.2 kilowatt other load. And infiltration, because this is a classroom, so students will be frequently coming in and going out initially, and during the class also there will be a lot of infiltration. So, infiltration is 10 meter cube per minute. Now, I have to find how much load is coming into the classroom. First of all, I will classify solar heat load, sensible heat and latent heat. Infiltration 10 meter cube per minute, 10 meter cube per minute air. Here the volume of the air is how much? Air volume is this is 0.9. So, 10 divided by 0.9, it is going to be 11.1 kg per minute, right. So, we have already done this exercise. This is the room condition. So, we will draw a vertical line from here and then we will get, this is the latent heat addition by the infiltration air, this is the sensible heat addition by the infiltration air. So, latent heat addition is 90 joules multiplied minus 59 joules. So, 90 joules, or this is 90 joules, or this one is how much? 59 joules. So, it is going to be 21 joules per kg and multiplied by 11.1. So 21 into multiplied by 11.1, it is going to be 233.1 joules per minute. So sensible heat by infiltration is going to be 233.1 divided by 60. It is going to be 3.9 kilowatt. Similarly, if you want to find the sensible heat addition by the air, infiltration air, enthalpy at this point is 48 and enthalpy at this point is 59. So 59 minus 48, this is the enthalpy difference, that is going to be 11 multiplied by 11.1. So 11 multiplied by 11.1 divided by 60. So the load will be around 2 kilowatt. Solar gain 5 kilowatt, glass 4 kilowatt, okay, occupants 60. 60 into 0.9, 60 into 0.9, 60 into 90 watt. So it is going to be 5.4 kilowatt. Sensible heat and latent heat is 1.8 kilowatt because 60 into 30 watt. So this is going to be 1.8 kilowatt. Tube lights 10, 40, fans 8, each fan let us say 90 watt, 0.7, other loads 0.2, infiltration we have already considered. So now we will sum this load. Now we will make sum of these loads. Now this you can do by yourself. Sum these loads, make sum of these loads, latent heat load. This will give you the total heat load. Now this sensible heat load and latent heat load, from here you can calculate the sensible heat factor, right. So once you have the sensible heat factor with you, let us say sensible heat factor is 0.8. Now 0.8 will be connected with this, 0.8 will be connected with this, and if you are using the fresh air, right, and if I say okay, I am using fresh air and I want to supply air to the room at standard 17 degree centigrade, right. So 17 degree, sorry, I want to supply room air to the 15 degree centigrade. So this sensible heat factor line, when it is extended, when it is cutting to this 15 degree centigrade, or maybe you may supply air to the room at 20 degree centigrade, or that is the designer's choice. Where it is cutting, that will be the supply point to the room. Now if I want to depict here for the sake of more clarity on this board, it is going to be like this. So this is the inside room condition, this is the sensible heat factor line, this is the inside condition, this is sensible heat factor line, maybe 0.7. I want to supply air to the room at 17 degree centigrade. So this is going to be my load line, because I have taken some imaginary values, so I am not getting exact point here. So this is going to be the load line. Now I have enthalpies at these 2 points, enthalpy at this point and enthalpy at this point. Now these two enthalpy points are with me, room load is with me, I can find how much air has to be circulated. I can find how much air has to be circulated in the room. Now there are other things we can find out from this information. In the next class I will solve one full-fledged numericals on the cooling load in a building, and then you will have clear insight of the phenomena. This is all for today. In the next class we will take one numerical example of cooling load. Thank you.